Okay, this is Chapter 12, Chemical Kinetics. This is Part 2 of actually the first half of the lesson. As I said, I am breaking it down into smaller parts, but you will need parts 1, 2 in order to complete the problem set. So we're talking about rate laws, and we are going to move to the method of what's called initial rates. This method requires that a reaction be run several times, and the data from the different trials is then used to determine the reaction rate. We vary the initial concentrations, and then we measure the reaction rate just after the reactants are mixed. Therefore, it eliminates the effect of the reverse reaction coming into play with equilibrium, as you know, is Le Chatelier's principle. And we use the data to determine the rate constant. So, how do we do this? Well, you choose two experiments such that all but one variable cancels out when divided. So you're basically setting up rate 1 divided by rate 2. So the change in the concentration of A divided by the change in the concentration of B. And what I tell students that it's easier if you put the larger initial rate on top, whatever experiment that is, and then the smaller initial rate on the bottom. So let's look at the example we have here of the ammonium ion and the nitrogen dioxide ion forming nitrogen gas and water. So we are going to use 1 or the average of all the experiments to determine the value of K, and then use dimensional analysis to determine the units of K. Now, I actually already showed you how to do this on a previous page in the previous lesson, but we'll do it again here. So I'm going to look and see where I have things constant. So in experiment 1 and 2, I have the initial concentration of NH4 constant. So I'm going to compare experiment 1 and experiment 2. And our initial rate should have the form rate equals K times the concentration of NH4 plus to the X, which is what we're trying to determine, times the concentration of NO2 minus to the Y. So experiment 1, our rate is 1.35 times 10 to the minus 7 equals K times the concentration of 0.1 to the X times the concentration of 0.005 to the Y. We're going to divide that by experiment 2, which is 2.7 times 10 to the minus 7 equals K times the concentration of NH4, which is also 0.1 to the X times 0.010 to the Y. We can see what happens here is that the K's cancel, this cancels. So when I divide through, I'm going to get 0.5 is equal to 0.005 divided by 0.01 is also 0.5 to the Y. Well, in solving for Y, therefore, Y equals 1. This becomes important. Now let's compare experiment 3 and experiment 2. So experiment 3, I have 5.4 times 10 to the minus 7 equal to K times 0.2 to the X times 0.010 to the Y. And I have 2.7 times 10 to the minus 7 equals K to the 0.1 to the X times 0.010 to the Y. Divide these through, and this cancels, and this cancels, and I get 2 is equal to 2 to the x, therefore x is equal to 1. So, a couple of things. We can figure out the overall reaction order. The overall reaction order is the sum of the exponents, which I taught you in the previous lesson. So that's going to be x plus y, which is going to be equal to 2. And we know that the rate is first order. So the rate equals K times the concentration of NH4 plus times the concentration of NO2 minus. So in order to calculate the rate constant, I can pick a rate, any rate, so I'll pick from experiment 1, 1.35 times 10 to the negative 7, and this is moles per liter dot seconds, equals K times the concentration of NH4, which we know is 0.1 to the 1, times 0.005 to the 1. And these are both going to be moles per liter. So I have a couple things going on. Let me just do the math first. So to solve for K, I've got 1.35 times 10 to the negative 7 divided by 0.1 times 0.005. So my K is equal to 2.7 times 10 to the negative 4. Now, for my units, I've got moles per liter dot seconds equals K times moles squared over liters squared. So once again, I did this for you before, liters squared, moles squared, these cancel, liters squared, moles cancels, liters. So I'm left with liters over moles dot seconds. So this is my answer to this. Okay, so let's just review. Integrated rate law. This law is used when a plot of concentration versus time is used. First order plot. If you're plotting the first order, it'd be the natural log of the concentration of A versus T to get a straight line. Second order plot would be 1 over the concentration of A versus T. And in a zero order plot, it's the concentration of A versus time to get a straight line. And you can just jot these graphs down if you want. Okay, here you've got the ln of A over time versus time, you get a straight line. Here you have 1 over A versus time, you get a straight line. And in the last one, you have the concentration of A versus time for a zero order reaction. Okay, moving on. This just reviews everything that we just did. Integrated second order rate law. Single reactant. 1 over the concentration of A equals KT plus 1 over the initial concentration of A. So the graph of 1 over the concentration of A versus T is a straight line with a slope of K. The half-life for a second order reaction, which you do not know how to derive, but is found in your textbook, is T to the 1/2 equals 1 over the rate constant times the initial concentration of A. For a second order reaction, Each successive half-life is double the preceding one. For zero-order reactions, rate is constant. It does not change with change in concentration. I mentioned this earlier. Zero order sometimes happens with catalysis reactions, which are enzyme-driven reactions. And the integrated rate law for a zero-order reaction is the concentration of A is equal to negative kT plus the initial concentration. And then your half-life for a zero-order reaction would be the concentration of the initial divided by 2K. So, how do we determine the order? We need to be able to do this on the calculator. So I'm going to give you some hints to help you do this, and it's fairly easy. Now, I do want to mention that you can also derive this mathematically according to the textbook, but I tend to do it in the calculator as it saves time. Plot the graphs of each and determine which line is the straightest. So, first thing you're going to do is you're going to go into Stat Edit, and you are going to enter lists. Okay? We're going to use 4 columns. I'm going to write them over here so it's easy for you to see. L1 is going to be equal to time. L2 is going to be equal to the concentration. You will populate those lists based on the data that you're given. L3 and L4 will populate on its own when you type in the equation. So L3 is going to be the ln, the natural log, of L2, and L4 is going to be 1 over L2. Very important before starting, you need to put the diagnostics on your calculator on. So if they're not on already, you have to go to Second Catalog, and I'm doing this for a TI 83 or 84. If you have a Nspire, you're on your own, or you need to talk to your math teachers. So you're going to go to Second Catalog, and you're going to scroll down until you see Diagnostics on. And then you're going to hit Enter twice. And you should see a message that says Done. This tells you that your diagnostics are now on and you're okay to proceed. Okay. Once we have our lists, we're going to quit. Then we're going to, it's not just quit, I'm sorry, it's second quit. Then you're going to go to Stat, Calc, Linear Regression, which is option 4, and you're going to check the correlation of R2 for each set of comparisons. So when we get to step E, we're first going to check L1, L2, then we're going to check L1, L3, then we're going to check L1, L4, and I'm going to walk you through this. The closer to 1 or negative 1 that your R value is, the straighter the line. The slope of the line will be the value of K. K is always positive, so if you get a negative slope, then the value is just the absolute value of the slope. Please note that in your calculator, the slope is equal to the A value. So I tend to make a habit of when I'm looking up the R values, I jot down the A values so that it saves me time. Okay, so let's go to our calculators, and what you need to do in this example is you're going to determine the rate law and the value of K for units of the reaction. So you know that the rate law has the general equation of rate equals K times the concentration of the species raised to the X. So you're going to go to Stat Edit, and you're going to go to your lists, and you're going to enter all of the times in list 1. So 0 through 400. Then you're going to go to list 2 and you're going to enter all the concentrations. When you get to the top of list 3, I want you to highlight list 3. Your cursor is going to be on list 3 and you're going to type in ln of L2 and then hit enter, and it will populate the list for you. You should get, for the first reading on top in that list, just as a check, you should get negative 2.303. You can stop and pause me at any time so that you can do this. Then you're going to go to L4. You're going to highlight it so that your cursor is on the top of it. And you're going to type in 1 divided by L2 and hit enter. And it will populate that list. And as a check, your top value should be 10. Once that's done, you're going to hit Stat Calc Linear Regression number 4. And you're going to type in L1, L2. And you should see an R value of negative 0.942. Now I didn't write the A value for this down, but you can write the A value down as you go through it. Then you're going to do the same thing all over. You're going to hit Stat Calc Linear Regression, and you're going to type in L1, L3. You get an R value of negative 0.999 with an A equal to negative 0.0069. Now I wrote down the A value for this one because I know already that this is the one that's closest to 1 because I've done it before. And then you're going to do it one more time, Stat Calc Linear Regression, which is number 4, L1, L4, and you get an R value of 0.94. So this clearly is the one that we're interested in. Okay, so what we want to do now, graph it. We want to graph it. We go to Second Stat Plot, and Stat Plot is right underneath your screen. You're going to choose number 1 and hit enter. Then you're going to select on. Make sure the cursor is on, and then you're going to hit enter. And then you'll be able to scroll down to X list and Y list. Your X list is always your time. Your Y list is always your ln of A. So if you recall, L1 is always time. So when you get to the X list, you're going to enter L1. Your Y list is your concentration. In this case, it's the ln of A. So you're going to enter L3. So for just this example, okay, you're going to enter L1, and then because we had chosen the one that was closest to 1, which was L3, we're going to put L3 here. Once you do that, you're going to hit the zoom button, and then number 9, which is zoom stat, and you should see a graph of a straight line. That confirms that this is a first order reaction. First order reaction has the form of ln of A is equal to negative KT plus the ln of A initial, where your slope is equal to A. So when I substitute in, I get the ln of A equals Remember it said the slope is positive, 0.0069 t plus the ln of A initial. Okay. Here's another example. It says determine the rate law and the value of K with units for the reaction. So again, just as a reminder, okay, you can pause me and do this on your own. You're going to do stat edit. In L1, you're going to be entering the times. In L2, you're going to be entering the concentrations. You're going to highlight the very top of the list where it says L3 and enter Ln of L2, and then hit enter, and it will self-populate that list. And then you're going to highlight L4, type in 1 over L2, enter, and it would self-populate that list. Then I want you to get your R values. You're going to do stat, calc, number 4, and you're going to enter L1, L2, and you're going to write down your R and A values. Then you're going to do that over, do L1, L3, write down your R and A values, and then you're going to do L1, L4. Pause me and come back and make sure that your R and A's match up with mine. Again, L1, L2, 903, L1, L3, 0.976, L1, L4, 0.999, with an A value of 0.0612. I didn't write these down because I knew that they weren't closest to 1. So, L1, L4 is simply, this is 1 over the concentration of A, which is second order. Had it been the ln of A, it would have been first order. And had it been L1, L2 as the straight line, it simply would have been the concentration of A, or zero order. A second order reaction has the form of 1 over the concentration of A is equal to KT plus 1 over the initial concentration. In this case, our rate is equal to the concentration of C4H6 squared. This is our integrated rate law. This is simply our rate law over here. So moles over liters dot seconds equals moles squared over liters squared, which I've already done for you several times. These cancel. And I'm left with liters over moles dot seconds. Okay, moving on. This is a really nice summary of the rate law equations found on page 548. You have rate law, 0 first and second, integrated, the plot needed to give a straight line, the relationship of the rate constant to the slope of the straight line, and then the half-life. So let's review. By getting the straight line, you can prove its first order, often expressed in a ratio. The half-life is the time required to reach half the original concentration. If the reaction is first order, then the ln of 2 is equal to kT to the 1/2, where the half-life is equal to 0.693 divided by K. So the time to reach half the original concentration does not depend on the starting concentration. This becomes an easy way to find K. Second order, our rate law is the concentration of A divided by the change in T. Second order, our rate is the change in the concentration of A divided by the concentration in T, where K equals the concentration of A squared. Our integrated rate law, 1 over the concentration of A equals KT plus 1 over the concentration of A initial. A straight line, if 1 over the concentration of A versus T is graphed, that's what you would get. And knowing K and the initial concentration, you can calculate the concentration of A at any time T. This is very useful. The second order half-life reaction, this basically tells you how it's derived. You don't need to know how to derive it. It's T to the 1/2 is equal to 1 over the rate constant times the initial concentration of the substance. In a zero order rate law, the rate is equal to the rate constant times the concentration of A to the 0, which is really the rate is equal to the rate constant. The rate does not change with concentration. This is the easiest one to deal with, but the one that they never ask because it's so easy. The integrated rate law is the concentration of A is equal to negative KT plus the initial concentration. And your half-life is equal to the initial concentration of A divided by 2K. Zero order rate law, most often when reaction happens on the surface because the surface area stays constant. And as I said earlier, this applies to enzyme chemistry or catalysis. So, using half-life equations, because we haven't worked with them yet, with the integrated rate law. A first order reaction is 38.5% complete in 480 seconds. Couple of things that we have to know here. We can assume, because that we're dealing with percent, assume 100% sample. The other thing that we need to do is we will always work with the remaining amount. So work with amount remaining. This is important. They told us it was a first order reaction, so we know that the rate law is going to have the form of the ln of A is equal to negative KT plus the ln of A initial. We know that it's 38.5% complete, so 100 minus 38.5 is equal to 61.5. So this is what we're working with, and we know that time is equal to 480 seconds. So the ln of 61.5 is equal to negative K times 480 seconds plus the ln of A initial, which would be, we started with 100, so the ln of 100. So the ln of 61.5 is 4.12 equals negative 480K plus the ln of 100 is 4.61. I subtract 4.61 from both sides and I get negative 0.49 equals negative 480K. And I get K equal to 0.00102 seconds to the minus 1, or 1.02 times 10 to the minus third. However you want to write it. So we have A. we need to calculate the half-life. We know that the formula for a first order reaction for half-life is equal to T to the 1/2, 0.693 K. So that's going to be equal to 0.693 divided by the constant 1.02 times 10 to the minus 3. And this is going to be 679.4 seconds. Moving along to C, D, and E. C, D, and E are solved exactly the same way, but you have different percent completion. Remember, we're not solving for the percent complete, but for the percent remaining. How long will it take for the reaction to go to 25% complete? So in C, if we have this formula, the ln of A is equal to negative KT plus the ln of A initial, we can solve by saying the ln of A over A initial is equal to negative 1.02 times 10 to the minus third T. And we can solve for T. So at 25% complete, that means that there's 75% remaining. So it's the ln of 75 over the ln initial, which was 100, equals negative 1.02 times 10 to the minus third T. Solving for T, you should get 282 seconds. Doing the same thing for D. I'm not going to rewrite the formula, except for now you're 75% complete, which means 25% remaining. It's the ln of 25 over 100 equals negative 1.02 times 10 to the third, negative third T, which means when I solve for T, I'm going to get 1,359 seconds. And for E, 95% complete is 5% remaining. And that's going to give me a T equal to 29:36 seconds. And that concludes the lesson. So you should have watched parts 1 and 2 to do the problem set for the first half of chapter 12.